How fragile matter emerges from extreme chaos at the Large Hadron Collider. In the most extreme laboratory conditions ever created, far hotter than the core of the Sun, matter appears to do something counterintuitive. Instead of fragile atomic nuclei surviving the inferno, physicists have now shown that they are born later after the violence has subsided. Experiments at CERN's Large Hadron Collider, LHC, have finally resolved a long-standing puzzle: how delicate particles such as deuterons and their antimatter counterparts can exist at all in such an extreme environment. When protons collide inside the LHC, they generate tiny fireballs with temperatures more than 100,000 times greater than those at the Sun's center. In this early stage, matter exists as an ultra-hot, dense soup of fundamental particles. Under these conditions, weakly bound nuclei like deuterons, made of just one proton and one neutron, should not survive. The force holding them together is simply too fragile to withstand the heat. Yet, experiments repeatedly detected both deuterons and antideuterons, posing a major challenge to existing theories. New measurements now show that these nuclei are not remnants of the initial collision at all. Instead, they form later, during the cooling phase of the fireball. As the system expands and cools, extremely short-lived, high-energy particle states, known as resonances, decay. These decays release protons and neutrons at just the right moment when the environment has become sufficiently calm for them to bind together. The same mechanism naturally produces antideuterons from antimatter components. According to the analysis, roughly 90% of the observed antideuterons originate from this delayed formation process rather than surviving the initial blast. The results were reported in Nature, a clearer picture of the strong force. This discovery provides important insight into the strong interaction, the fundamental force that binds protons and neutrons inside atomic nuclei. As Professor Laura Fabbietti of the Technical University of Munich explains, the findings demonstrate that light nuclei do not emerge in the hottest phase of a collision. Instead, they assemble later, once temperatures and particle densities have dropped. This resolves a key inconsistency between experimental observations and theoretical expectations. Beyond nuclear physics, the implications extend into astrophysics and cosmology. Light nuclei also form naturally in space, for example, when cosmic rays collide with interstellar matter. Antideuterons in particular are considered potential messengers of exotic processes, including dark matter interactions. With a more accurate understanding of how these particles form, scientists can refine models used to interpret cosmic ray data and better distinguish ordinary physics from possible new phenomena. Recreating the early universe at CERN, located near Geneva, operates the world's most powerful particle accelerator, the 27-kilometer-long Large Hadron Collider. By smashing protons together at nearly the speed of light, the LHC recreates conditions similar to those that existed microseconds after the Big Bang. These experiments allow physicists to probe matter at its most fundamental level and test the laws that govern the universe. One of the LHC's flagship experiments, ALICE, a large ion collider experiment, is specifically designed to study the strong interaction. Acting like an ultra-precise three-dimensional camera, ALICE can track and reconstruct thousands of particles produced in a single collision. This capability enables researchers to follow how an initially chaotic state of quarks and gluons cools and reorganizes into stable forms of matter. From subatomic particles to cosmic structure, the work is part of a broader research effort within the Origins Cluster of Excellence, which investigates how structure forms across all scales, from elementary particles to galaxies and life itself. Closely connected is the Collaborative Research Center SFB 1258, which focuses on neutrinos, dark matter, and the fundamental forces of nature. Together, these studies highlight a striking lesson from modern physics. Even in the most violent environments imaginable, order can emerge, but only at the right time. Fragile nuclei do not survive chaos. They are created after it, once the universe, even on the smallest scales, begins to cool and settle.